Hello, my name is Alexander Kreis and welcome to my talk at the German Probability and Statistics Days 2021. I'm going to talk about a joint project with Ingrid van Keilechoom from the KU Leuven, in which we use Laguerre polynomials for semi-parametric estimation and measurement error problems with an implication to epidemics. Let me show you in a picture what type of situation we have in mind. So in the beginning of a pandemic, we can have two locations. First location here, a location where the virus is not spreading yet, and another location where the virus is already spreading. On the bottom here, we have a timeline. And what we observe here, we suppose are two people in the location 1 where the virus is not spreading yet. And at time point 0, one of these two people is traveling to location 2, while the second person is remaining all the time in location 1. Then at time point T1, the first person gets infected with the virus. And at time point S1, this person shows symptoms. Here I depicted that at the end, but it could also be somewhere here in the middle of this chain. Then at time W, the person travels back to location 1 and at time point T2 meets the second person and infects the other person, such that the other person shows symptoms at time S2. Since the virus has not been circulating in location 1, we can be sure of two things. Firstly, that the first person got infected while being in location 2, and secondly, that the second person got infected from person 1. In these situations, one normally does not observe the times T1 and T2. Yeah, so we don't see when the infection actually happened. We only observe the travel window W and the two symptom onset times. Moreover, it is of interest to estimate the incubation time, I1, which is the difference from the infection to the symptom onset. So we have it here for the first person and an incubation time I2 for the second person. Also of interest is the so-called generation time G, which is the difference of the two infection times. But as you can see, all of these quantities cannot be directly observed. However, here, as a reminder, you have again the timeline. We can see that the symptom onset times S1 and S2 can be written as sums of the incubation periods and the generation time and the first infection time. So that S1 and S2 are sort of convolutions of the quantities of interest, and this is what we will use for estimation. But let me first show you our modeling assumptions. So we suppose that W is distributed with density phi W. Then we have a random variable C, which determines the location of travel. So on the previous slide, I've only shown you location 2 as potential travel location, but in the model, we allow that there are several travel locations which have density PC. So this is a discrete probability density independent of W. Then the first infection, T1, is supposed to have a density T1 conditionally on the length of travel and the location of travel. And we suppose that this density is distributed on the travel window 0W, and the location here comes as this exponential rate into play. Yes, so this can say, is it more likely that the infection happens in the beginning of the window, towards the end of the window, or if R is equal to 0, then with a uniform distribution of the infection time. Then the incubation periods have density phi I, which are independent of all the previous random variables, and the generation time G has a density phi G, also being independent of everything else. So now what do we want to do? So we suppose that we have observations, the following observations, IID copies of the two symptom onset times, of the travel length and the travel location. And our objective is to find non-parametric estimators phi I n hat and phi G n hat of the density of the incubation period and the density of the generation time. The contribution of this project is that we do non-parametric estimation. Previous work was focusing mainly on parametric models for these two densities. But we think that non-parametric estimation can be interesting for the following reason. If you consider, for example, estimation of the basic reproduction number R0, then one way of doing that is by using the Euler-Lotka equation, which gives R0 as by this formula. Here phi G is the density of the generation time and R is the exponential growth rate of the expected incidence. And if this is the only thing you're interested in, then we think that a valid estimator could be to take a non-parametric estimator for phi G and just plug it in here to get an estimator for R0 hat. Yeah, and so here using a non-parametric estimator gives you extra flexibility because you're not bound to a parametric model. And if this function is smooth enough of the density, then it could still, this estimator for R0 could still have good properties. So this is our motivation for studying non-parametric estimation. So how are we going to do that? We do this by the method of thieves and define to this end functions phi theta, where theta here is an n+1 dimensional vector, and phi theta is defined on the non-negative real line, exponential weight, and here a weighted sum of the first m Laguerre polynomials. So Lk is a case Laguerre polynomial squared. And then you can show that this function phi m is a density whenever the theta has Euclidean norm equal to 1. And the proof is based on the fact that Laguerre polynomials are orthogonal with respect to the exponential weight. So then GM now defines the space of all the densities of this degree. Here, with weights having Euclidean norm 1. So that this is a good approximation, I try to convince you from that by that in the next on this slide. So it can be shown firstly that the union of all GM lies dense in the set of the smooth densities. And here let me show you 2 examples. So the solid line here is a log normal distribution, and here a Weibull distribution, and the dotted lines show the best approximations of densities of the type as shown before with various degrees. And you see here that already from degree 2 onwards, we have fairly good approximations. In particular here, the log normal distribution, which starts with a flat bit, can be, this flat bit here can be well captured already with degree 2. Okay, so now how do we do the estimation? We just do maximum likelihood. So the likelihood is given by this, which I don't want to discuss now. And what we're doing is now we take just for given degrees m1 and m2, we find those functions phi I and phi g as estimators, which maximize here this likelihood where phi I theta 1 and phi g theta 2 come from the respective approximating spaces. And what we can prove for this estimator is the following. So we have a consistency result in our paper. So we can show that if you choose m1 and m2 of the order n to the power beta, where beta here is related to gamma to a gamma by this relation, then we have that the Hallinger distance of the density of the observations. So f phi I phi g is a conditional density of S1, S2, and W given C. So if you recall that PC is the density of C, then this is a joint density here, or the true joint density of the observations. And this here is the joint density of the observations if you plug in the estimated densities. So the Hallinger distance between these two converges to 0. Yeah, no faster than n to the power minus gamma, where gamma here is related to the beta, but also not faster than the Hallinger distance between the true incubation time density and the best approximation. So phi in here is the best approximation of order m1n. And similarly, it can also not be faster than the Hallinger distance between the true density of the generation time and the best approximation of the generation time in the space GM2. Now you might say that here we only have density, the density of the observations and not the densities phi I and phi g directly. But under further regularity assumptions, we can also prove consistency of these estimators directly. And this, yeah, as I've said in the beginning, so this is similar to the deconvolution setup. So here we need similar assumptions concerning the characteristic functions, which I don't show here for time reasons. If you choose in the previous theorem m1 and m2 to be of the order n to the power 1 over 5, then you will get here as a best possible rate n to the power minus 2 over 5 if the functions are smooth, if the true densities are smooth enough. And finally, of course, it will be of interest to get an asymptotic normality. But so we see that this is more difficult. And so what we've just shown is only the first step to that. So here's further research required. So we do this currently. I'm working with Ingrid on another project where we want to do estimation of quantile regression, quantiles under censoring. So there we try to also get asymptotic normality. But I will try to convince you here in the simulations that this is an interesting or a promising further step to do so that the estimator is actually asymptotically normal. So just a quick word about the proof. So what we need to do is we need to find the covering numbers of the sieve spaces. We need to show that the approximation quality of the GM is sufficiently good, and then we can use a result from Wong and Shen to prove the consistency. So let me now show you in the last minutes some simulations so that we consider this data generation process. I don't want to go through the details. Just let me say the density of the incubation period is a log normal distribution, and the density of the generation time is a Weibull distribution. And we choose all parameters to sort of resemble a data set of Ferretti et al. So that this is hopefully a kind of realistic data generating process. This data set has 40 observations. So we also choose here 40 observations. And then we do one simulation. We use then on this data set the BIC to choose a model, which is in this case M1 equal M2 equal to 2. And then we use this for 100 further repetitions. And we see here is a solid line for the incubation period and generation time. In both cases shows the true density. The dashed dotted line shows the best approximation from the Laguerre spaces, and the gray lines here shows the estimators. And what you see here is for the incubation period, this works quite well. For the generation time, there's a bit more fluctuation, which is not so surprising because the incubation period is sort of observed twice per pair. And so 2 people, so 2 incubation periods, well, there's only 1 generation time. However, even though here this estimate appears to be quite wiggly, if you want to estimate the basic reproduction number R0 in a fictional pandemic, where we choose as the incidence growth rate R to be log 2/5, so doubling every 5 days, we still see that the estimate works quite well. So here the dotted line is a true R0, and the histogram here shows the estimated values. The solid line here is the density of a normal distribution with the sample mean and sample variance. So here we see that this is actually quite motivating and promising to motivate that our estimator for R0 is indeed asymptotically normal, so this should be worth exploring further in this direction. Yeah, that was it then from my side. I've just here some references which were quoted during the talk. The details to the theorem which I've shown you can be found here in our paper, which you can find on arXiv. So that was it then from my side. I say thank you very much for watching this video. And if you have any questions, I will be more than happy to answer them in the Q&A session, or you can send me, of course, an email all the time. Thank you very much for watching, and I hope to see you at the conference. Goodbye.